In this video, we're going to talk about rates of change, or speed. It's a very important idea in calculus. In fact, a vast majority of the material we're going to cover in this course involves rates of change. We're going to talk about two different types of rates of change here: average rate of change and instantaneous rate of change. The average rate of change is an idea that you've talked about in previous courses, and it's a fairly straightforward idea. Let's say, for example, you're going to go on a bike ride and you ride 10 miles in 40 minutes, which is 2/3 of an hour, and you want to calculate your average speed, which is a rate of change. It's a fairly straightforward calculation. We can use a formula: distance equals rate times time. So this is a formula saying that if we know how fast we're going and how long we travel at that speed, we can find our distance traveled. And since we want to find our speed, we can solve that equation for r, and we get rate equals distance divided by time. Plugging in the information we know, 10 miles divided by 2/3 of an hour, we know that over that 40-minute time interval, we averaged 15 miles per hour. However, this 15 miles per hour can be a misleading number. It doesn't mean that we traveled 15 miles an hour the entire time period. It just means that over the length of those 40 minutes, we averaged 15 miles per hour. It's more likely that we spent quite a bit of time traveling less than 15 miles per hour and quite a bit of time traveling more than 15 miles per hour. So, a more interesting concept with rate of change is instantaneous rate of change. This can be a much more valuable idea. So, in our bike example, let's say we want to know how fast we're going at any particular moment. That would be considered our instantaneous rate of change. However, to calculate instantaneous rate of change, we need a lot more information, and we're going to need some different methods. So here's an example, and this example includes the more information that we're going to need. We're riding our bike, we coast down a hill, and because of gravity, we're going to be accelerating. We're going to start going faster and faster as we go down the hill. So coasting down a hill, our position can be represented by the equation s equals 3t plus 2t squared, where s is the distance you have traveled in meters, and t is the amount of time in seconds that have passed since you were at the top of the hill. So the question is then, what is our speed after exactly 2 seconds in meters per second? So the units we're going to use to measure our speed are going to be meters per second. We can't use the same equation, but we can use a similar equation here. We know that our average speed is equal to our change in position, so change being represented here by the Greek letter delta, position being represented by the letter s. So the average speed can be represented by the equation, the change in position divided by the change in time, or the amount of time that we're traveling. Or more plainly written, we can evaluate our position at 2 different times and divide it by the amount of time, or the difference in times, over that interval. However, this equation is not immediately useful to us because we need, in this equation, 2 separate times. And we want to evaluate what our speed is at exactly 2 seconds after we leave the top of the hill. If we tried to plug 2 seconds in for t1 and t2, we can see in the denominator here we're going to get 2 minus 2, which is 0, and we can't divide by 0. This is where we're going to have to come up with some new methods. So here in our bike example, we know our position after any amount of time, we know how to calculate our average speed, and we know how to do that over a time interval. So we're going to go ahead and do that. We're going to measure our average speed over a time interval, and we're going to see if that can be useful for us. We're going to involve intervals that have t equals 2 in them, and see if we can establish a pattern that can allow us to answer the question. So to start with, we're going to look at our average speed over a 1-second interval. So starting at 2 seconds and going until 3 seconds, let's see what our average speed is. So we'll plug in the numbers. We know that we've traveled 13 meters in 1 second. So over that time interval for 1 second, our average speed is 13 meters per second. Now we know that's not our instantaneous rate of change. We're looking for the rate of change at the beginning of that time interval. So to make this a more accurate answer, to get it closer to what we're actually looking for, we're going to make the time interval shorter. Instead of going for 1 second, we'll go for 1/10 of a second. We'll start at 2 and go to 2.1. Plug in the numbers. and we end up getting an average rate of change over this interval of 11.2 meters per second. Again, this is an average, but it's closer to the number that we should be getting here at exactly 2 seconds. And we can continue making the time interval shorter and shorter and shorter. So 100th of a second, 1,000th of a second. And we see these values, 13, 11.2, 11.02, 11.002, are approaching a number. They're getting closer and closer to a number without giving any sign that they're going to go past it. So we can see here that our average speeds are approaching 11 meters per second as our time interval gets shorter and shorter and shorter. This idea here, as one quantity approaches a number, as another approaches a number, is the idea of a limit. And this limit is going to be central to all of calculus. So a limit, the language of a limit here in this particular problem will say that as the time interval approaches 0, our rate of change approaches 11 meters per second.